Okay, so now we can start what I was telling you last time. Let me just remind you. So basically the idea that we were talking about equivalence relations, right? And we did some examples, with the behavior of the students, like one of those. The point of an equivalence relation, that what makes it useful is that you can it allows you to break up the original population. We can use the word population instead of set if you prefer. You break up the original population into pieces, and those pieces are known as like a partition of the original set. Okay, now what I was saying is that there is a very important example of this class of an equivalence relation, which is the one that we were starting to talk about the last time, and that involves vector spaces. So the setup that we had last time is that you had a vector space. Let me see if I can draw the picture again. Um, Again, there's not like a great picture here, but you have like a vector space, and then you have like a smaller subspace inside of it, right? So it's still like a vector, what you call like a vector subspace. So here you have a vector subspace. Okay. And the idea is that you can define an equivalence relation by saying that two vectors are related if their difference belongs to the subspace. Okay, so what we have written is that V1 is related to V2 if V1 minus V2 is in the subspace. And it's very easy to convince yourself that that would be like an equivalence relation. Okay, there was an example I gave you last time. Let me see if actually I try to fix this. Right, so the example from last time was like if we thought of the largest vector space at R3, and then the smaller subspace is R2, right, which kind of like sits inside R3. And so what we have said is that, what does it mean for two vectors? What does it mean for the difference of two vectors to be inside R2, right? If you kind of like the condition for being in R2 is on the xy plane is for the third coordinate to be 0, right? So that can only happen. Here I was just checking that it was an equivalence relation, but the idea is that the only way for those two vectors for the difference to be in on the xy plane is that if they have the same height, if they both have the same height, right? So that's geometrically what's happening. So again, like the idea of the point of an equivalence relation is that you break up the space into pieces or like into different region subsets. So the idea is that two vectors are related if they have the same height. So height is kind of like the property that distinguishes one equivalence relation from the other. Height is kind of like the distinguishing feature. In the same way, in which when we're talking about the students having the same major, having a particular major is a distinguishing property, like from one group of students to another group of students. So here the distinguishing feature is having having if you have different heights, you are not related to one another. So what I was telling you is that the equivalence classes in this case, you can refer to an equivalence class just in terms of like its height. And so there like z can take any values on the number line. So like the equivalence classes can be represented by the z-axis in this picture. So that's kind of like what's happening in this case. But what is the z-axis in this? Is from this perspective, you can think of it as the orthogonal complement to the xy plane. So I'm just gonna like I know we talked a little bit about orthogonal vector subspaces or orthogonal complements in linear algebra, but I'll give you kind of like a quick refresher. And also I'll give you some examples that maybe you haven't seen before, which are kind of like fun with functions and other things. Just to kind of like give something new in case you have already like if you know this story pretty very well. Okay, so the goal for today is to understand the equivalence classes of this relation. Okay. So for that, again, I'll need this idea of like the orthogonal complement. So let me tell you about that. So again, hopefully it's like a refresher. What is the orthogonal complement to a vector subspace? Well, there's not like a great picture you can make, but the idea is that I'll say in a moment why this is a bad picture. So, sorry, I should have called the purple one W. So if you think of like W as being a subspace, right? W paired, which is sometimes like how you refer to the orthogonal complement, it just consists of all the vectors that are orthogonal to the vectors in W. Okay, so here like I'm kind of like thinking that both of these live inside a larger vector space, which again I cannot draw too well, but you know. But the idea is like the orthogonal complement. So W perp. So this is called the orthogonal complement of W. And again, it consists of all the vectors which are orthogonal. Again, orthogonal is just like another way of saying perpendicular to all the vectors in W. So the idea in this picture is that if you had a vector here, which is you can call, well, actually, let me make it look more perpendicular. If you had a vector U, and then you had a vector W, right? Their dot product being 0, you can just say that's another way of saying that they are orthogonal. What's happening here? Okay. Whenever U is in U perp, W perp, sorry.
and W is in the vector subspace W.
The reason why I'm saying is that this picture is not that great is because, it feels like, it looks like they are intersecting, but the only intersection between the two is the zero vector, right? Because if a vector lives, like I'll make this as a remark, right? If a vector simultaneously lives in the vector subspace W and the orthogonal complement that is perpendicular to itself, the only vector that's perpendicular to itself is like the zero vector. So let me, let me write that down, that this is a misleading picture.
The previous picture is misleading because the only vector that belongs both to W and its orthogonal complement is the zero vector. Right, because again, like because if U dot U is zero, like that's what it would mean for it to be on both of them. And that means that it's orthogonal to itself. But what is like the product of a vector with itself is just it's like square. So is that okay? Is that making sense? Okay, so now what I want to do for a couple minutes is just like give you some interesting examples. Um, so because again, this is like a very important idea. So the first thing to say is something about matrices. Like, what is the correct definition of the transpose of a matrix? Again, like since you may have taken like, very different classes. I'm not sure whether you have been told this or not, so I feel kind of my duty to kind of make sure we're on the same page. So what is the proper definition of the transpose of a matrix? By the way, I'll add some problems. Now that we covered this material, I can put some interesting problems for you to look at, or that we can, there's some fun ones. So what is the interesting, the correct definition? I'll put correct in quotes, like not to sound too kind of condescending. So what is the correct definition? So, okay. Let me start with the down to earth version of it, right? Like the down to earth version of the transpose is that you switch rows with columns. The rows becomes columns. So that's kind of probably like the version that you have been taught, just in linear algebra. Right, so the first row becomes the first column, just in this case, like the second row becomes the second column. So in terms of like size, it's always nice to, it's always good in these cases to do like a rectangular matrix because it's easier to see kind of like some of the differences. So the matrix A is 2 by 3, right? The matrix A transpose is 3 by 2. So definitely this is important, right? Like the transpose does swap the size of the matrix, right? So in general, if A was n by n, right? So if A was n by n, the transpose does become n by m. Okay, that is one of the important problem. But to kind of like understand like the correct way to define the transpose, you do have to think of the matrix more as a linear transformation. which is something you may or may not have seen like in linear, like I think you to do that in linear algebra to some extent. But what is the idea of like, let's start with A, right? So A is a 2 by 3 matrix, right? So it can be multiplied by a vector that has size 3 by 1, right? Like the vector, you can do, you can do A times V, where like, let's say the vector V has 3 entries, right? Because this is 2 by 3, right? And this is 3 by 1, and the sizes match, and so you can do the multiplication, and you end up with something 2 by 1, right? So you end up with a vector of 2 entries, right? So from this perspective, you end up with x plus 2y minus z, and then you do 4x plus 5y plus 0z, which is just 0, right? So that would be the the way you could do the matrix multiplication. But if you think about it from that way, like the input, right? Like what this is saying is that you can feed a size 3 vector to the matrix and it spits out like a size 2 vector, right? So a way to think about this matrix is that you can give to it a vector with 3 entries and it produces a vector with 2 entries, right? So let me do that more like as a diagram. Again, here you have like the vector with 3 entries. And the matrix, you can use a matrix to produce a vector with 2 entries, okay? Which you're calling A times V. Right, so from that perspective, and that's kind of like like a little bit more like abstract way of thinking about the matrix. It's closer to a function, right? Because it has a domain, which is R3, and it has a range or like a codomain, which is R2, because it produces 6 vectors with 3 entries, produces vectors with 2 entries. And in fact, if you kind of like think about it in the general case, right? And again, this was for like this was for a 2 by 3 matrix, right? So in the general case, it's kind of confusing at the beginning, but it kind of like when you have like a M by N matrix, right? When you have an M by N matrix, again, like if you want to do the matrix multiplication with a vector, then you have to do an N by 1, right? So like this has starting in Rn and it ends up in Rn. Right, because like that's the only way for the matrix multiplication to make sense. So this vector now has N entries. So what you need to remember is that like kind of like the starting point is kind of like the second number and the ending point is the first number, which is kind of sometimes confusing the first time you see it because it's maybe the opposite way of how you would like that. Okay. That making sense? So far, so good. Question. Okay, and now once you have that perspective in mind, you can kind of like give the proper definition of the transpose, which I'll do it with this diagram. So the idea, the correct definition of the transpose is that, again, if you have the matrix A, which is M by N, again, that starts in Rn, and you go into Rm. And then the transpose, I do want it to go, I do want it to swap the sizes, so it kind of like goes in reverse, goes backwards. Right, because the transpose is N by M. So it kind of like each a vector of size n and will produce a vector of size n. So you can kind of like think about it in terms of the diagram of just going in the opposite direction. Okay, so the idea is that what you can do is that you can start. Okay, let's follow the diagram. You can start with the vector v. If you use the matrix A, oops, sorry about that. If you use the matrix A, you get A times V, right? And okay, you get A times V, which and let's say that you have another vector which I'm calling to call U here. So maybe let me use a different color so that it's not confusing. And then you have another vector U that lives in Rn. Now these two vectors, because they have the same size, you can take their dot product, right? So you can take the dot product of A times V. Dot the vector U. Okay. So the transpose, like the property that the transpose is supposed to have, is that if you take the vector U and you go backwards, right? Because if you take the vector U, you get like if you want the transpose to have the opposite size, you can apply the transpose to U and it would land somewhere in here. So you can take the transpose. Right? And now because A transpose U is on Rn, you could also take the dot product with V. So that the transpose is actually defined so that those two dot products end up being the same number. I'll kind of show you what I mean by that. So the transpose has the property that if you take the dot product on this side or you take the dot product on this side, you get the same result. In terms of a formula, what that looks like, if you just focus on the formula for a second, let me, where am I? If you focus on the formula for a second, it's kind of like swapping the matrix. So the matrix here was on the first factor, right? It was on the first factor. What the transpose says is that, okay, you can move the matrix A to the second factor, kind of like move it to the second factor, but the price that you pay for moving it to the second factor is that you have to transpose it. You're allowed to move, you're kind of like allowed to move the matrix around from the first factor to the second factor as long as you transpose. And that actually covers, you can kind of like go check the details. The usual definition that they give you of like changing rows with columns does have like the property. It does satisfy this. But like in words, what I'm saying is that you can move the matrix from the first factor to the second factor as long as you transpose it. Okay, so you can move one of the factors to the other. but okay, kind of like example. That is why, in a sense, like if you think about symmetric matrices, that is why they're so important because from this perspective, if the matrix is symmetric, that means that you pay no price for moving it around because A equals its transpose, so you can put it wherever you want and it's still kind of the same matrix A. So you can kind of move it back and forth. Yeah.
Is it a consequence of transpose or like our definition of transpose?
It is actually like the correct definition. But if you put that definition with the standard dot product on our end, that forces like the thing about the rows and the
So
columns.
it's like from a bilinear form.
Right.
It's the
Exactly.
adjoint.
Right, it's like kind of like what you would call the adjoint. Yeah. Actually, one of the examples I'll do is kind of like for like the derivative operator. What's the transpose of the derivative operator? You just have to do like a like an inner product on the space of functions, and then you find. But if you use this correct definition, you have to do integration by parts and other things, and you'll find that it's minus itself. It's very fine, like kind of weird calculation. And that actually is important for Fourier series and other things that like having the transpose like in more generality. I was going to do like an example similar to that in a moment, but yeah, like this is like that's why I was saying this is like the correct definition, and then with this correct definition, you prove kind of like as an exercise that on our end that correspond like that literally just corresponds to swapping the rows with the columns, you see. This is actually like this it makes so there's this fundamental theorem of linear algebra. What is the fundamental theorem of linear algebra? The rank nullity theorem. Okay, so let's see if you remember like this. But it becomes very easy to understand from this perspective, you know. So here's like the instead of the fundamental theorem of calculus, right? Like the fundamental theorem of linear algebra. Well, I'm not going to write all of it now. I'm just going to write kind of like part one or part two, whatever, if you want. Let's just call it part one. So if you had a matrix, right? Let's say that you have like a matrix which is n by n. You can find it's like the null space. I'm just trying to use the terminology which is also called the kernel. Like so, you have something called the null space. Let me write it down. So you have an n by n matrix, right? And again, from my diagrammatic perspective, that means that it starts on Rn and it ends on Rm. Okay. So when you have a matrix, there are two vector spaces or subspaces that are kind of like attached to the matrix. The first one is the null space, which is all the vectors that solve the homogeneous system, A times X or A times B equals 0. Okay, so the first important vector space associated to the matrix A is the null space, which again is also called the kernel. Like, if you open like almost any math book, they usually call them the kernel. You usually just write that as kernel of A. And those are like all the vectors in Rn for which which solve the homogeneous system. Okay. And it's very easy to check that this forms a vector subspace because if you have two solutions to a homogeneous system that solves the homogeneous system, if you multiply a solution to the homogeneous system times a scalar, that also is a solution to a homogeneous system, right? And that vector space it actually lives inside Rn because there are the vectors in Rn. So again, just to kind of draw it in a picture, here you have the null space. And each dimension is called like the nullity, like, you know, like the nullity is the dimension of this vector subspace. And the dimension of the kernel or the nullity of the null space is the dimension of the kernel, which is just the nullity of the matrix. So hopefully that rings a bell when you were solving Gauss matrix systems of equations with Gauss-Jordan. You would row reduce it, and from there, like, you could kind of figure out those things a little bit easier. And then another, so that's the first important vector space that you can associate to a matrix. Another one which is important is okay, called like the what, like the range or the image of the matrix. Oh, I'd actually would that's what you would call the column space there, right? Like I'm just trying, sorry, so sorry. Like I always try to remember like the terminology. So like the other one is called like the sorry. Right, because like let's see, if the matrix is like, that's why it's always useful to kind of like do the concrete example, like which is the one, because right, like the columns, right, that's why it's always useful to put like a rectangular matrix, right? This matrix is 2 by 3, so the columns have size 2, right? So the column space lives on R2. Okay, yeah, so we're good, back to normal. So yeah, the other important space, of the matrix is called okay, comes under different names, but probably the one that you're familiar most with is like the column space of the matrix. Which you would write as col of A. That's also called the range of the matrix. Is that's more if you're thinking of it as a matrix as a linear transformation as a function. So because it's usually you talk about the range of a function. So that's where that one comes from, or just the image of the matrix. But like again, like maybe just going from like the perspective of the column space, because hopefully that's the one that is most familiar. The column space was all the vectors that are linear combinations of the columns of the matrix, right? But being I mean, if you can like work out like the different interpretations of matrix multiplication, being the column space means that it is kind of like you know, when you write a system as A, B, like, or AX equals B, you know, if this system could be solved, what that meant is that the vector B is a linear combination of the columns of A. That was one of the matrix interpretations of the matrix multiplication. So they could like just to use like the notation that you probably know more. These are the vectors in Rm for which the system AX equals B has a solution. Okay, so the point here is that the column space lives in Rm. Now and then, from this perspective, like because the transpose goes backwards, right? Because the transpose goes backwards. Let me use a different color. So if you see like from this diagram, the important thing from this diagram is that kind of like the null space and the column space live on the different worlds, right? Like on the different items. So if you go backwards, kind of like the picture gets flipped. So here lives the null space of the transpose. This is where the null space of the transpose lives, and here's where the column space of the transpose lives. But what is the column space of the transpose? Is the row space of A. Like that's why they call it, because row space and column space, the column space of A transpose is the row space of A, basically. So here you would have you would have like the null space of A transpose, and here you would have the column space of the transpose, but the column space of the transpose is the row space of A. Because the transpose, as we were discussing, like, it does involve just like flipping the rows into columns. Is that okay? Making sense so far, so good? Okay, and then one of the, so, if you ever have seen like, there's like this famous like mathematician at MIT, Gilbert Strand. So he got like some, if you go to MIT, they have like this open courseware where like you can watch like some of their old videos. And so he got like a very good series, like, like from linear algebra back in the day. I mean, he's still like, teaching there, which is insane because he must be like nice, like, he's old, like, but he's so nice. So his book, if you buy his book, it has like a front cover of like basically this diagram. Like the front page, like the cover of the book of his linear algebra book is that, and that's what he calls like the four fundamental subspaces of linear algebra. And in fact, the book in the book is a little bit better drawn kind of like drawn more like how I have them here, where they kind of like more like seem perpendicular to one another, and it is because they are perpendicular to one another. So kind of like one of the things that the fundamental theorem of algebra says is that the orthogonal complement that they're kind of like the orthogonal complement of the null space is the column space of A transpose or like the row space, and the orthogonal complement the column space is the null space of A transpose. So let me write that down, which we'll actually need that next week. So what the fundamental theorem of linear algebra says, I'll copy paste this picture. Yeah, like the fundamental theorem of linear algebra says that like that, for example, the orthogonal complement to the null space that the orthogonal complement to the null space is the row space of the matrix, or like, the column space of A transpose, which is just the row space of A. And then the orthogonal complement to, it doesn't matter which one you do it, like, let's say like the orthogonal complement of the column space. I'm just doing it this way because that kind of like refers to the matrix A. So the orthogonal complement of the column space is the null space of A transpose. Oh, sorry, like that's the green one. Oh, I forgot to say that, like, like the dimension of the column space, right, is just like the rank of the matrix, right? So you can define, like, again, like, that's probably not the way it's defined in linear algebra at the beginning, because you start in that class, by row reducing matrices. But, in a more like kind of like elegant way. In a more elegant way, you can kind of like define the rank as the dimension of the column space of the matrix. Now, what that, like, of course, we're not going to be getting to the proof for this because, like, this kind of like a tangent to our course. But I kind of like what goes into the proof. One of the key ingredients that goes into the proof is actually showing that the rank of A is the same as the rank of A transpose. So that's kind of like key there. But what I was going to show you is that it is super easy to see why they're perpendicular subspaces, and that is super quick with the definition of the transpose that I gave you. So I just wanted to do that to illustrate that why it's nice to have this elegant formula for the transpose. Okay. So this one, like the proof would use like rank of A is the same as rank of A transpose. But what I do want to show you is that it's very easy to see, but it is very easy to see why they are prepared, like why, for example, the null space and the column space are perpendicular to one another. So why is, but with our definition of transpose, it's easy to see why they're orthogonal. These subspaces are orthogonal. So why is that? I'll just show you that quickly for I think it's easier to see why these two are orthogonal. So why are these two orthogonal? Why is the column space orthogonal to the null space? So why is well, let's just think about what each of them mean. You know, oops. If this is the column space, right? And you have a vector inside the column space, like, well, this is the definition that I have on the board. If you have a vector in the column space, that means that this system of equations could be solved. That's the definition of being in the column space. That there is a solution to this system of equations. Another way of thinking about it is that you can write the vector b as a times x. Okay, so this vector b can be written as a times x. For some vector x, there could actually be more than one vector that works, you know. But the point of is that anyone in the column space is of the form a times x. And then if you have a vector in the null space, right? I'll just call it u. Well, like, you know, if you have a vector in the null space, what does it mean to be in the null space of A transpose? It just means that it solves a homogeneous system of equations, but for A transpose. Right, that's what a null space is. That's the solution to the homogeneous system. So that means that this vector u solves A transpose times u equals 0. So this one solves A transpose times u equals 0. Okay, so I want to show that the dot product of B with U should be 0. But what is the dot product of B with U? So what is B dot U? That would tell me that they are perpendicular to one another. Oops. That would tell me that they're perpendicular to one another. So basically B, by assumption, you can write it as A times X. Okay, and then I use the magic property of the transpose. The magic property is that you can move it to the other factor at the price of putting a transpose there. So you can move it to the other factor of the dot product if you transpose the matrix. But then you're you're done because A transpose U is zero because of the fact that U was in the null space of the transpose. So this one is a zero vector. Right, and the dot product of any vector with a zero vector is automatically zero. So I like those like one line proofs of things like from linear algebra, right? Like it's kind of like boom, like immediate. And there you go. So I mean, the point is just to kind of like to illustrate that it kind of like gives confidence that this is like a good definition because like a good definition to some extent kind of like simplifies proofs, you know, so it makes kind of like the proof like a one liner that at least they are perpendicular. You still we have to check that the rank, like this thing about the ranks, if you want like a full proof of the fundamental theorem of linear algebra. So there's obviously other things that you would need to do, but it's understanding why they work, they have to be perpendicular. Yeah, becomes very, very simple. So this is like a good example of like, you know, this is kind of like the most important example from linear algebra of like the orthogonal complement of a subspace because like matrices obviously are like very important like linear algebra. But in general, you know, you can have like a vector subspace, you know, just going back to what I was saying earlier, you know, you can have like a vector subspace. You know, this was kind of like an aside, but you know, back to like our situation. If you have a subspace, I'll try to draw it like this. If you have a subspace, then you have the complement, the orthogonal complement. It does look perpendicular, but again, not that great. It's hard to make like accurate pictures in this case, but at least it's accurate in the sense that they just touch at the origin. Like the only two vectors that the only vector that they share is like the origin. So their intersection, if you want, is just a zero vector. So the important thing about the vector subspace and its complement, orthogonal complement, is that they have complementary dimensions in the sense that the dimension of W plus the dimension of the complement adds up to the total dimension of the vector space. So and because their intersection is only the zero vector, also what that means is that if you have a vector in the larger space, there's a unique way to write it as a sum of two vectors, one in each of these pieces. So if you have a vector v, let me maybe write it like this. If you have a vector v, which is completely random, there's a unique decomposition of this vector v as a sum of a vector, like I'll write it v perp. Well, let's see. Well, let me write it as VW perp. It's like a lot of like notation here, but and another vector VW. So kind of like it's kind of like a project. I mean, this is related to the projection and everything, you know. But if you have a vector, there's kind of like a shadow that it makes on the subspace, and there's like a complementary shadow that it makes on the orthogonal complement. But the idea is that because they all intersect at the origin, that way of writing it is like unique. So any vector v can be written uniquely. Any vector v can be written uniquely as a sum oops, I'm sorry about so this one is the first one is in W and the second one is in W perp. Okay, here's like a fun before like, just to give you like a more interesting example, because like we will also want to analyze these sorts of things. So here's like an interesting example of like a vector space. Um, let's say that you have the interval. Okay, I'll make it symmetric for my purposes. So let's say that you have the XY plane. So here's like a more like interesting example. So let's say you have the interval, I'll just do it from -pi to pi. Right, so when you have like, if you have like that interval, if you have like a function defined on that interval, right? It could be even or it could be odd, right? Like the function could be even. So. So like like the example, like an even one, like just like looks symmetric with respect to the y-axis, right? Let me see if I can do something kind of like that looks symmetric, right? Like that could be like an even function, right? This could be an even function. And the other one kind of like involves like a reflection, right? Like so a function was even, f was even if f of x was f of -x, right? And it was odd, if f of x is minus f of minus x, right? So kind of like something similar to x cubed would be a good example of like an odd function, right? Does that look kind of, it kind of looks like odd to me. Okay, so this one would be odd, and f of x is minus f of minus x, right? So that's kind of like, this is an even function, and this is an odd function. So here's like a fact that you may or may not know, that any function, like again, like I'm just focusing on this interval, right? But it's not that, like there's nothing special about this interval yet. But I do want the interval to be symmetric because otherwise this property wouldn't necessarily make sense to us. Like if a function is even or odd, if the interval is not symmetric about the origin. But kind of like an interesting fact is that any function on the interval from negative pi to pi is like a sum of an even and an odd function. Let's see if that makes sense. So like any function. So here's my first claim. Any function on the interval from negative pi to pi is a sum of an even and an odd function. The matrix analog of that is that any square matrix is a sum of a symmetric and an anti-symmetric matrix. So like, I don't know if you have seen like the, well, probably know what a symmetric, you do know what a symmetric matrix is because are used very much in linear algebra. Like a matrix is called skew symmetric or anti-symmetric is like the transpose is minus itself. Okay. So it's kind of like the symmetric matrix is kind of like similar to even, and the skew symmetric matrix is kind of like similar to being an odd. So, like the linear algebra analog is that any square matrix is a sum of a symmetric and a skew symmetric matrix. Okay, so I'll do the almost one of the like kind of all the tricks in the books like to show this super silly, but it's kind of like very clever. So it's kind of again like one of these like 1 minute proofs, which is what really fun. So let's see. Here's my one-liner. Basically, it's almost one line. Okay, this seems silly, right? Like any fun, it doesn't matter what function you have, you can always write it as, f of x over 2 plus f of x over 2, right? Like that is totally fine, right? Just because 1/2 plus 1/2 gives you 1. So you really haven't made anything there. Okay. And then you can do, oh my God, I hope that I'm doing it correctly. So oh, right. And then I will add and subtract f of negative x. I think that's a trick. I'm kind of like, That makes sense because again, like, did I do anything? No, I just added zero. It's just like I'm adding zero in a very weird way because these two cancel out. This is just zero. I'm just kind of like writing zero in a very odd way. But what happens here? This is kind of like 1/2. Let me see if I can kind of like collect terms. So this is 1/2 of f of x plus f of negative x plus 1/2 of f of x minus f of minus x. Right, like, so I just put this one as the first term and this one as the second term in here. By the way, let me write here like the matrix analog. The matrix analog is that if you have a matrix that's the same as A over 2 plus A over 2, right? And that's the same as, maybe that one is easier actually. This is the same as A plus A transpose over 2 plus A minus A transpose over 2. That's kind of how, if you were working with matrices, that's how it would look like. Again, it's fine because A over 2 and A over 2 add up to A, and A transpose minus A transpose cancels. So you really have the same as A there, right? But what can you say about the first function? That is an even function, right? Like f of x plus f of minus x, like that's even, like there's almost nothing to check, and this one f of x minus f of minus x is actually odd. So that kind of like lets you write this as a sum of an even function and an odd function. And again, like for matrices, like maybe let me just put it here for matrices, in case someone like wants it. And the first one is symmetric matrix, right? This is because if you transpose it, you get A transpose plus A transpose transpose, which is just A. So this one says symmetric matrix and this one says asymmetric. So this is kind of like the same idea. So I'm almost done, just to kind of give you the punchline of the example. So here's like an analogy, which I think is like a useful analogy to think about. So like, here's like an analogy. So like, this is probably something like in computer science or discrete math could be like a different notation that you use. No, but when you have a vector with n entries, kind of like the way that we write it to refer to its entries is like v sub 1, v sub 2, v sub n, right? Kind of like what you would call the index. I mean, there is not much of a difference between that and writing this as v of one or v of two, v of three, v of n, right? Like, so where do you place the one, you know? It kind of like, it's clear in both cases what you mean, right? Like, this is like, just means that the first entry of the vector, the second entry of the vector, the last entry of the vector, it doesn't matter it doesn't matter too much. It doesn't matter too much whether you put it as a subscript or just like next to it. But this is like a more suggestive interpretation, right? Because it's kind of like more like a function notation, right? This is kind of like a function notation. So from this perspective, you know, you can think of this as a that, if you think about it kind of like in an analogy with the function, right? It's being defined on 1, 2, and n, right? So from this perspective, a vector is just like a function from the set from 1 to n into the reals, right? Because each of them is a real number, right? This is a real number, this is a real number, this is a real number. So from this perspective, if you have a function, kind of like in discrete math, if you have the set 1, 2, 3, 4, 5 up to n, right? Just like the finite set, right? Like a finite set. And you have like the number line here, right? And I asked you, what is a function from this finite set into the number lines? Like a function is just like an assignment of a number to each of these elements, right? So the number one has to go somewhere, which you call v of one, right? So this is v of one. The number 4 has to go somewhere, which you would call v of 4. The number n has to go somewhere, which you would call v of n, right? So from this point of view, like a vector is just like an ordered list of numbers, right? That's what a vector is. But from this perspective, you can also think of a vector as kind of like a discrete function, because it's just like a function from the finite set 1 to n until the reals. So from this perspective of a vector, so from this perspective, a vector is a function. Oops. So instead of you calling it f, which is like the traditional name for a function, in this case, like it just happens that you call it v, right? Does that make it kind of like like it takes some time to get used to it, but it's like a very useful analogy to have, because when you think about their dot product, right? If you think about their dot product, I'm almost done. I'll finish here, like just at least to suggest this idea, right? If you have the dot product, which was u dot v, right? If you have two vectors u dot v, like dot product was u1 v1 plus u2 v2 up to un vn. But from this perspective, well, first you can go to calc2 and use the sum notation for the for this. So it's a sum from y equals 1 to n of ui vi, right? And then if you go back to this function notation, instead of writing u sub I and v sub I, you would write u of I and v of I, right? So you would rewrite this as a right? But if you take n to go to infinity, right? You thought, oh, if you think of kind of like a discrete is kind of this being a finite version of a function, right? The only difference is like a function is f of x, so it has a continuous index. X takes continuous values. Here, like the values are discrete, they jump. But if you think about a function, if you just kind of like as a notational change, if you change I into x, right? then you would like to define kind of like a dot product between these two functions as, oops, sorry about that. I'm almost, I'll continue this next time, but you would want to define something like kind of like involving f of x, g of x, right? But then it also involves a sum, but you kind of like it's a continuous sum, like so the way to do a continuous sum is by integrating, so replace the sum with an integral, right? By the way, this is not the notation that people use for like the dot product between functions. You just put kind of like in parent, but I'm just trying to make the analogy a bit more clear. And then it's with the x, and then there you go. So that is a definition, that is like the genuine, that is like the actual definition of like, well, here you have to put bounds of integration, let's say from negative pi to pi, just because that was the example I was working with. But that is like the genuine gut, like honestly gut definition of the dot product between the functions. But it is just like a natural extension from this perspective. If you think of a vector as a function on a finite set, so it becomes a continuous function, like, and then so a function in a sense, from that perspective is a vector with a continuous index, which is kind of a useful idea. And what will happen, I'll tell you, I'll put this probably as an example so that you can check it, is that that there's a subspace of odd functions, which is orthogonal to the subspace of even functions. But you can check that the sort of an even function is perpendicular to an odd function. So if you do Fourier analysis, you probably have seen that, because when you go to Fourier series, it has decompositions of sines and cosine. And you can check, for example, the sines and the orthogonal to the cosines and stuff like that. Well, let's finish here. I'll tell you, we're getting to almost there to the first application of the course, which is for these like ranking problems, kind of like the Netflix ranking and all this stuff. But it's almost that, like a few more like things that I have to get out of the way. But I think they with that, I'll post a problem for you to look at, which are kind of fun.